x of t is a impulse sampled value and it came out to be whichever way you take it. This is the definition of the discrete Fourier transform, where xn is the sample values spaced at interval equal to some t, and then these are the frequency samples of the spectrum spaced at a interval equal to twice pi by t and sampled at values integral multiples of 0 to 0, 1, 2, 3. In the 102, we have defined the inverse transform as equal to 1 by n but now we are a bit more intelligent than what we were at 102. So, I can now show that this is indeed the inverse transform of this, because this function is the orthonormal function. So, we are expanding this in terms of orthonormal series, finite orthonormal series, and so the coefficient can be obtained, the x of n of this coefficient can be obtained by multiplying by e to the power of on both sides and summing it over this on both sides, then you will find that this product of this and that, when you sum it up, will come out to be an orthonormal series. So, as a result of that, we will end up into xn being equal to this. Okay. So, that you can check it up at home if you want, because e to the power of j 2 pi by n m minus k sigma over k is only is equal to 1 equal to n for m is equal to k, 0 for m not equal to k. Okay. So, this is the result that results into this definition. You can check it up at home if you want. Okay. We call this function as a w is equal to e to the power of minus j 2 pi by right. In 102, we define w as equal to e to the power of minus j 2 pi by n. So, we could write this in terms of the w function, and then we showed that this is nothing but a matrix relationship where x0 remember this. So, same equation I can write in terms of the matrix rotation here, and then we also use the relationship that w n plus k is equal to w k. So, we simplified this by using this relationship, and then we found something very interesting, that if I do a shuffling of these values recognize these values in a specific manner, and then this matrix can be written down as equal to, remember your FFT is what I am doing, is equal to 4. Yes, sir.
I just wanted to come. You carry on.
So, this one is broken down into 4 parts, where this is equal to some f of n minus n by 2. This is f of n by 2 of size n by 2 multiplied by some matrix here, which is representable as equal to D into a diagonal matrix into other matrix. And similarly, this, except here you get a minus sign here. That means, if n by n matrix we broken down into n by 2 matrix, and n by each n by 2 matrix again can be broken down into similar manner n by 4 matrix. So, finally, you ended up into only 2 elements at a time, and I gave you the butterfly diagram for the fast Fourier transform, right. And all this became possible only because of this cyclic property of elements in the matrix. So, we found that how to find Fourier transform by using this so called fast Fourier transform algorithm by Cooley and Tukey, and it reduces the time of computation from n square to n log n, right, and the memory that is required also comes down from n square to log n. The 2 advantages, memory requirements also comes down, as well as the speed of computation also increases. So, everybody now uses this Cooley-Tukey algorithm for finding the Fourier transform, and Fourier transform is a universal recipe, everybody requires it. So, it has become very popular, this Cooley-Tukey algorithm. And now, as I told you in 102, it is even available as a button in your oscilloscope in the laboratory. You transform on that by using the button. And the button, when you press it, what it does is basically Cooley-Tukey algorithm. So, it has become very popular, and as a result of that, it happened in 1960-61 time scale, and then a lot of craze, and everybody worked on this fast Fourier transform. Umpteen number of papers are published, and then people try to do some amount of twinkling around with it, and then try to say that my speed has increased, decreased by slightly a delta here, and so many papers are published. But basically, the idea here is to use the Cooley-Tukey algorithm, which is a result of this fundamental property of the cyclicity of the sinusoidal waves, which somebody recognized it, and so it became very popular. Now, all this has the assumption that the number of samples is some 2 to the power of n, some m, and something I must use 2 to the power of p, right. All the samples are 1024 or 512 or 256 or 64 or 32 or something like that. It has to be 2 to the power of something. And then this algorithm works beautifully. Okay.